3 zebra mussels. That is all it takes to seed a new infestation. 3 thumbnail-sized mollusks clinging to the hull of a boat, surviving a 2-hour drive overland in a bucket of bilge water and dropping into a new lake before anyone notices. By the time a monitoring team pulls their first sample and confirms the species, the colony beneath them already numbers in the millions. The United States has been fighting this animal since 1988. It has spent, by the federal government's own accounting, more than $5 billion trying to slow it down. Poisons, barriers, surveillance networks that span 46 states, and the zebra mussel has not retreated a single watershed. Soy Tom Marsh. And this is the story of 3 native species that did what $5 billion could not, and what their return tells us about the one mistake every human-led solution keeps repeating. The first thing you need to understand about Dreissena polymorpha is that it doesn't belong to any of the systems it has destroyed. It evolved in the Ponto-Caspian Basin, a cluster of ancient lakes and rivers straddling what is now Ukraine and Russia, where it has natural predators, natural competitors, and a ceiling on how dominant it can become. There it is, one thread in a web. Transport it to the Great Lakes, to the Mississippi Basin, to the reservoirs of the American Southwest, and you remove every single constraint that kept it in check. What you are left with is a filter feeder with no ceiling at all. And filter feeding is, in the calmest possible terms, an ecological superpower. A single adult zebra mussel can process up to a liter of water per day. A colony, dense enough to coat the bottom of a lake bed, which is exactly what they form within a few years of arrival, can filter the entire water column of a moderate-sized lake in a matter of days. That sounds beneficial until you understand what they are filtering. They are removing phytoplankton, the microscopic algae at the base of nearly every freshwater food web, stripping it from the water column before native species can access it. They are essentially eating the foundation. Lake Erie is the case most scientists return to when they want to show what this looks like at scale. Before zebra mussels arrived in the late 1980s, carried in the ballast water of transatlantic cargo ships, Lake Erie had water clarity of roughly 1.5 feet in its western basin. Turbid, algae-rich, productive. Within a decade of the infestation taking hold, water clarity had increased to more than 12 feet in affected areas. That sounds like an improvement. It is the opposite. Water that clear means the phytoplankton is gone. The zooplankton that fed on it collapsed. The fish populations that depended on the zooplankton followed. The native mussels, already in decline from decades of pollution and habitat loss, were outcompeted for space and suffocated under layers of zebra mussel shells. In the western basin of Lake Erie, scientists documented the near total disappearance of several native mussel species within a single decade. Multiply that across the Mississippi River system, which now connects to the Great Lakes through the Chicago Canal, across the Tennessee River network, across the glacial lakes of Minnesota and Wisconsin, and you begin to understand why the number reaches 5 billion and keeps climbing. The management response has been essentially a permanent emergency. States have funded boat inspection stations at every major lake access point. The Army Corps of Engineers has poured resources into barrier technologies. Researchers have tested everything from chlorine to potassium to targeted molluscides, always running into the same problem. You cannot poison a mussel selectively, you poison the lake. This is where the story shifts. And it shifts not in a boardroom or a laboratory, but in a shallow stretch of the upper Mississippi near La Crosse, Wisconsin, in the late 1990s, when biologists working on a separate project made an observation that didn't fit the narrative anyone was writing. The zebra mussels in that stretch were dying. Not from a chemical application, not from a drought or a temperature event. They were being eaten. The species doing it was the freshwater drum, Aplodinotus grunions, a native fish that most recreational anglers consider a nuisance, a rough fish, the kind you toss back without a second thought. It has a set of molariform teeth in its throat. Flat crushing teeth evolved specifically for processing hard-shelled prey. Biologists had known about this anatomy for decades. What they had not tested, because no one had reason to before 1988, was whether the drum would apply those teeth to an invasive species it had never encountered in its evolutionary history. It would, and it did. Stomach content analyses published through the U.S. Geological Survey's work in the upper Mississippi found freshwater drum with zebra mussels accounting for a significant portion of their diet in areas where the drum population was healthy and the mussels were present. The fish did not eliminate the infestation, but in stretches where drum populations were intact, the mussel density was measurably lower than in stretches where the drum had been heavily fished out over the preceding decades. That last clause matters more than anything else in this story, where the drum had been fished out. Here's the thing about the freshwater drum that $5 billion of management strategy never fully reckoned with. It didn't disappear from these rivers because the zebra mussel outcompeted it. It disappeared because we decided it wasn't worth keeping. Decades of commercial fishing pressure, bycatch, and the cultural designation of the drum as a trash fish had reduced its populations in precisely the rivers and lakes that would later be devastated by the invasion. We removed the predator before the invader arrived, and then we spent decades trying to replace the predator's function with chemistry. But the drum is only one thread of this. The second species is less glamorous than even the drum, which is saying something. The lake sturgeon, Acipincer fulvescens, is one of the oldest vertebrate designs still swimming in North American freshwater. It has been here in essentially its current form for more than 100 million years. It can live for over 150 years, and it is a bottom feeder of extraordinary scope, vacuuming invertebrates from the substrate, including mussels, including zebra mussels, with a protractile mouth that works like a biological vacuum hose. Lake sturgeon were commercially fished to near extinction across the Great Lakes and the Mississippi Basin between roughly 1,860 and 1,920. They were considered a nuisance fish first, so abundant that their bodies clogged fishing nets and were burned in piles on the shore. Then they became a delicacy, and the fishery collapsed within 2 generations. By the time zebra mussels arrived in the late 1980s, lake sturgeon populations in Lake Erie had been reduced to roughly 1% of their historical abundance. The ecological function they had performed for 100 million years, processing vast quantities of benthic invertebrates, was simply absent. Reintroduction programs for lake sturgeon have been running since the 1980s in several Great Lakes tributaries, led by a coalition of tribal nations, state wildlife agencies, and federal partners. The work is slow because the species is slow. Sturgeon don't reach reproductive maturity until their mid-teens at the earliest, and the full return of a self-sustaining wild population takes decades, not years. But in rivers where restoration work has been sustained long enough to produce measurable results, the data has started to arrive. Research, published in the Journal of Great Lakes Research, documented that in tributaries where sturgeon reintroduction programs had been running for more than 15 years, the fish were appearing in sections of river with zebra mussel colonization and showing direct evidence of mussel consumption. More significantly, the benthic community structure in those sections was beginning to diverge from control sections where sturgeon remained absent. With lower zebra mussel density and early signs of native mussel recovery in microhabitats, it is not a reversal. No one is claiming that. The scientists working on this are careful, appropriately careful, about the scale of what they are observing. But it is a directional signal, and in conservation biology, a directional signal after a century of loss is worth more than almost anything else you can produce in a laboratory. And this is where the story gets to the part that nobody planned. The third species is not a fish. It is a bird. And it was not reintroduced anywhere near the Great Lakes for the purpose of zebra mussel control. It arrived on its own, following its own logic, and the consequence it produced was not on anyone's management spreadsheet. The lesser scaup, Athia affinis, is a diving duck. It winters in large numbers on the Great Lakes, and it eats zebra mussels, not as a fallback option. as a primary food source in areas where mussels are abundant. Waterfowl biologists at the USGS had been tracking an anomaly in lesser scaup body condition for years. Birds wintering on the Great Lakes were showing lower fat reserves and poorer condition than birds wintering elsewhere, despite having access to what appeared to be an abundant food supply. The zebra mussel, it turned out, has poor nutritional quality relative to native mussels and invertebrates. It is calorically thin. The birds were full but not nourished. That story, troubling in its own right, contained an observation that reframed everything else. In areas where the scaup were concentrating in highest numbers, the local zebra mussel density dropped by a documented 40 to 60% over a single winter season. According to studies conducted by USGS Great Lakes Science Center researchers in the early 2000s, a single flock of wintering scaup, thousands of birds in some cases, could restructure the mussel bed in a shallow bay more effectively than any chemical treatment, and without poisoning anything else in the water. The scaup didn't solve the problem. They were being nutritionally harmed by it, but the scale of their predation pressure, applied passively, seasonally, without coordination or cost, exceeded the localized effect of most managed intervention programs. 3 species. A rough fish nobody wanted, a prehistoric bottom feeder we almost burned to extinction in the 1800s, a diving duck that was eating the wrong thing and suffering for it. None of them were deployed as a strategy. 2 of them were present because of long, difficult restoration work. 1 of them showed up because that is what its species has always done in winter. And together, in the watersheds where they overlapped, they were doing something that $5 billion of human management had not managed to do. They were exerting sustained, distributed, energetically free predation pressure on an invasion that no chemical could touch without collateral damage. There is a word that keeps appearing in the scientific literature around this convergence, and the word is redundancy. Ecological redundancy. The idea that a healthy system doesn't rely on a single species to perform a function. It has 3 or 4 or 10 species that can perform variations of the same function, so that if one is lost, the system degrades but doesn't collapse. What the zebra mussel invasion exposed, in the cruelest possible terms, was how thoroughly we had stripped that redundancy from the Great Lakes and the Mississippi Basin before the invader ever arrived. We hadn't just lost the drum, or the sturgeon, or the scaup in their historical range. We had lost the entire guild of invertebrate consumers that, together, could have done what no single species and no single management program can do alone. A study published in the Proceedings of the National Academy of Sciences, examining long-term biodiversity and invasion resistance across freshwater systems globally, found that ecosystems retaining higher native species richness showed significantly greater resistance to invasive species establishment and spread. The mechanism wasn't predation alone. It was the full suite of competitive interactions, space occupation, resource consumption, and behavioral interference that a complete native community exerts on any new arrival. An empty niche is an open door. We had been opening doors for decades before the mussel walked through. This is the part of the story that makes the $5 billion figure both more understandable and more difficult to defend. The money was never going to solve the problem, because the problem was not the zebra mussel. The zebra mussel was the symptom. The problem was an ecosystem so hollowed out by a century of extraction and species removal that it had no immune response left. You cannot buy back an immune response. You can only rebuild it slowly, 1 species at a time, and then wait for the functions to reassemble. That is what the drum is doing in the upper Mississippi, where drum populations have recovered under protective fishing regulations introduced in several states over the past 2 decades. That is what the sturgeon is doing in the tributaries of Lake Erie and Lake Michigan, where reintroduction programs have been running long enough to produce adults. That is what the scaup is doing every winter without anyone asking it to. There is a word for a place in Wisconsin that I want you to hold on to: Winnebago. It comes from the Ho-Chunk language, and it means roughly people of the big water, or murky water people, a reference to the turbidity of the lake, the productive phytoplankton-rich turbidity that the zebra mussel is now stripping away. The word survived the near destruction of the culture that coined it. The lake it described is still fighting to survive what we brought to it. But in the shallow bays, where the scaup concentrate in November and December, and in the tributaries, where the first sturgeon have begun to return, the water is doing something it hasn't done in a long time. It is being used the way it was built to be used by the animals that evolved to use it. We didn't restore those bays with a check. We restored them by giving back a fraction of what we took and then staying out of the way long enough for the fractions to add up. That is the thesis this canal keeps returning to, because the data keeps confirming it. We did not restore the ecosystem. We returned a few of the species that knew how to, and what happened next was not our doing. The question I want to leave you with is this. If a rough fish that nobody wanted, a prehistoric dinosaur we nearly burned to extinction, and a diving duck eating the wrong food for the winter are outperforming $5 billion of managed intervention, what does that tell you about where the next $5 billion should go? I have my answer. I think you might have yours too. Tell me in the comments, because this is one of those conversations that doesn't have a clean ending, and it shouldn't. If this story shifted something in how you think about what fixing nature actually means, share it with someone who needs to hear it. There are more stories like this one than most people imagine, and I have many more to tell you. Soy Tom Marsh. Thank you for watching.